Hello everyone! Today, we're going to explore an innovative memory technology, Resistive Random Access Memory or ReRAM, and learn how it is implemented and applied in the Nuvoton M2L31 series microcontroller. Resistive Random Access Memory, or simply ReRAM, is the focus of today's lesson. In this session, we'll go through the following topics in order: the key features of ReRAM, the programming process, the programming time, the memory protection mechanism, and the corresponding configuration settings. In traditional NOR flash, data must be erased first before it can be written, a process that takes at least 20 milliseconds. However, the ReRAM used in the M2L31 series eliminates this requirement, allowing data to be written directly without an erase step. As shown in the comparison chart on the upper right, when updating 4 kilobytes of data, the M467's NOR flash takes about 136 milliseconds, while the M2L31 ReRAM completes the same task in only 44.8 milliseconds. That's a 65% reduction in update time, greatly improving the efficiency of firmware or data updates. So, what exactly is ReRAM? Its principle is based on changing the conductive state of the material through set and reset operations, representing the digital values 0 and 1. In the M2L31 microcontroller, thanks to the characteristics of ReRAM, it provides a 512 kilobyte capacity with a dual bank architecture and supports word-line programming. Unlike traditional flash memory, it allows direct writing without the need for an erase operation. Moreover, even in power-down mode, ReRAM maintains ultra-low power consumption, making the system both energy efficient and highly reliable. Now let's take a look at the key features of the M2L31 series. It comes with a built-in dual-bank ReRAM, supporting secure firmware upgrade and memory remapping, offering up to 512 kilobytes of AP-ROM and 8 kilobytes of LD-ROM. In terms of security, the M2L31 series supports 4 XOM regions for code protection, as well as a 2 KB OTP block for one-time programming. For reliability and performance, it supports 32-bit and word-line ReRAM programming, includes a built-in CRC32 checksum, and integrates a cache memory, effectively enhancing performance while reducing power consumption. Regarding the dual bank architecture of the M2L31 series, it utilizes read-while-write, which is RWW technology. This allows the system to erase and program bank 1 while executing code from bank 0, ensuring that the CPU can continue running services without interruption during firmware updates. In addition, a rollback mechanism can be implemented through software design. If a CRC error occurs after an update or the system fails to enter the main loop, the firmware can automatically revert to the previous version, ensuring stable and reliable system operation. So, how does ReRAM actually work? Unlike traditional NOR flash, ReRAM follows a unique write sequence. It must first clear the data buffer, then load data into the buffer, and finally perform the programming operation. You can think of the data buffer as an internal cache within ReRAM. It temporarily stores data before the write process completes. In operation, ReRAM supports both single-word and word-line programming. The difference lies in how data is loaded into the buffer. In single-word mode, data is loaded only once. In word-line mode, the data buffer can be loaded repeatedly up to 64 times, with each load containing 2 words, MSB and LSB, allowing up to 128 words to be programmed in a single operation, greatly improving write efficiency. It's important to note that word-line programming requires page alignment to ensure data is correctly written. In terms of programming time, according to the datasheet, single-word programming takes approximately 300 microseconds per word. In contrast, word-line programming requires only about 39 microseconds per word on average, showing a significant improvement in performance. We also conducted practical tests with several data patterns, and the results show that the average programming time per word using word-line programming is much shorter than that of single-word programming. Therefore, in real applications, if page-level writing or updating is required, it is recommended to use word-line programming, which can significantly reduce the overall programming time. Here is a list of all the commands used for memory operations. If a specific function is needed, you can refer to the corresponding command details in this list. In terms of command operations, the programming sequence typically uses commands like 2F, 27, and 21 to perform clear, load, and program, respectively. In Nuvoton's BSP, you can find the relevant APIs in the rmc.c file. By using these APIs, you can complete the entire programming process without manually sending commands. This list shows some of the commonly used APIs. One point to note is that, to maintain consistency with other Nuvoton MCU series BSPs, the Erase a Page API here actually writes all bits to FF rather than performing a traditional erase. Next, let's introduce the memory protection features of the M2L31 series. To prevent accidental modification of program areas, each RMCAPWPROT bit can protect a specific 8 KB data block. Within these protected regions, users cannot perform any write or update operations. Only a mass erase can clear the data. The relevant settings can be found in Config 8 and 9 under AP-ROM Safety Protect, while the Config 10 provides the AP-ROM Write Protection Lock level and the Write Protect Lock pin to further enhance security. These mechanisms ensure that firmware and data are fully protected during operation, preventing unexpected overwrites. Let's take a closer look at the Write Protect levels for memory. As mentioned earlier, each RMCAPWPROT bit protects an 8K bytes data block from accidental overwrites. For finer-grained protection, the Write Protect level in Config 10 determines how strict the protection is. The protection levels range from level 0 to level 3, with higher numbers indicating stronger protection. Level 0 is the lowest protection and the default setting. Config values can be modified via ISP, and the protection registers can be controlled by software. Mass erase is allowed. Level 1 starts restricting CPU write access. Software cannot modify the protection, but mass erase is still permitted. Level 2 and Level 3 rely on a specific external Write Protect lock pin to determine whether protection is locked and if mass erase is allowed, providing maximum security for sensitive or high-security applications. These settings provide a flexible yet secure protection mechanism suitable for different use case scenarios. Another special protection feature is the Secure Conceal function, designed for secure hiding. A common use case is to protect the encrypted sections of a bootloader. Once execution in this area is complete, the region is fully concealed, and if the program attempts to jump back to it, the system will immediately trigger a hard fault. Enabling this function requires 2 steps. Step 1, configure config 4, 5, and 6, the status becomes enabled. Step 2, after enabling, jump into the conceal region and set the SCACT register to 1. Only then is the region officially active. Within the Secure Conceal area, both data and instructions cannot be written by the program, and only a system reset can clear it. This feature is particularly important for custom bootloaders, as it protects encryption routines and critical code, ensuring that after exiting the bootloader, the region is completely unreadable and non-executable. This shows the config regions that need to be set for the Secure Conceal function. In the Secure Conceal function, enabled and activated are 2 distinct states. About the enabled, the CPU can still access the region normally. Access from ISP or PDMA is blocked, but the system does not generate errors. As for the activated, the conceal region is fully active. If the CPU tries to execute code in this area, it triggers a hard fault. PDMA operations are halted, and ICE debugging cannot read the region, ensuring it is completely hidden. In short, the enabled status is a preparation state, while the activated is when the protection is fully enforced. The only way to exit the activated mode is through a system reset. To learn more about ReRAM features, please refer to the example code available at the paths mentioned above. That concludes our introduction to Resistive Random Access Memory. If you have any questions, please feel free to contact us. Thank you.